Okay, now welcome to video class 49, and in this video we are going to study about controllability and observability. And in this session, first I am going to explain what is controllability and observability. This is the ability of a system, and finally we will be dealing with the test by which you can test whether it is controllable and observable using, and that test is called as Kalman's test. Okay, so the Kalman's test for controllability and observability, and this is the last topic under this session. Okay, so we'll see what it is. So before going into that, a linear system can be represented by state space model as x dot is equal to ax plus bu, while the output y is given by cx plus du, where A is called as the system matrix, B is called as the input matrix, C is called as the C is called as the output matrix, and D is called as a coupling matrix. Okay, now now let us see what is the term, the meaning of controllability. It is the in a very layman language, it is just the ability to control. Okay, that is what I meant to say is, say so you have a system with the inputs and some states x1, this is u, and this output y. Okay, now if it is possible to control the state of the system input, okay, the state of the system via this input, then they are said to be controllable. Okay, right? Hope you understood. That is, using this input, if it is capable of controlling the states of the system, then that system is said to be controllable. Using this input, you must have a control on the state, so that that's under control. I mean, that's not going to get affected by the different states of the system. Now, on the other hand, you have something called as observability. Observability, it is, if you know the output, from the output you will be able to assess the internal states of the system, okay, or the initial state of a system. When the output is known, that is called as observable. Okay, so using this input you will be able to control the state, then that is called as a controllable. If you have if the by the knowledge of the output, if you can assess the initial states of the system, then we call it as the observable. Now to be more technical, you can say a system is said to be controllable. A system is said to be controllable if it is possible to find some input signal. Say your input signal, here you are using some input signal u of t, which will transfer the initial state from x of t0 to x of, say, some t dash or t1, okay, to another desired state. Okay, so if there are some inputs which are capable of changing the initial state x of t0 to some other desired state, then that system is said to be controllable. And that's what is the definition of controllability. By using the input, you can change, you can control the states. Okay, so such a system we call as the controllable system. Okay, now when can you call a system as completely controllable? When a system is said to be completely controllable if all the initial states can be controlled by using the input signal to any desired signal. Okay, So all the states to, I mean, we can change all the initial states to a desired value by using the input. Then we call as the completely controllable. Okay, now there is a controllable criterion. That's what is important. Okay, now consider a system with the state. We have already considered the state equation AB, and from this, for to check the controllability, you must have to develop as a matrix called as QC, right? A composite matrix, a composite matrix QC. Okay, and that QC is defined as like this. It starts with the first element will be B, second element will be AB, the third element will be A square B, the fourth element will be A cube B, and so on up to A n minus 1 B, right? Okay, so what is this n? N refers to the order of the system. Okay, say for example, if it is a second order system, your QC will be having how many? It will be B, right? A into B, and you don't have A2 because it is 2 minus 1 A1. So this is it. Now if it is a third order system, then your QC matrix will be B, then the next element will be A into B, the third column will be A square B. Okay, right? So this is the first step for the for checking the controllability. Now after finding out this controllability, we can check the rank of this QC. That's the procedure, rank of QC, right? And if the rank of QC is equal to the order of the system, then that system is said to be controllable. Okay, and if it is not equal to the order, then that is not controllable. Now the rank of matrix, how to see the rank of matrix n of an n into n composite matrix. The rank of the matrix is n. The rank of matrix is n if the determinant of this QC, okay, is not equal to 0, right? Is not equal to 0. If that is, if QC is not equal to 0, if the determinant of QC is not equal to 0, then the rank of this matrix QC, the rank of QC will be always equal to the order. Okay, and if this is satisfied, then that system is controllable. So, or in other words, what you want to see is you just need to prove whether the determinant of this QC is 0 or not. If it is not equal to 0, then that is controllable because that becomes equal to the n order of the system. And if it is not equal to 0, if it is equal to 0, meaning that it is less than, the rank is less than the order of the system, meaning that system is an uncontrollable system. Okay. Now, similarly is the case with the observability. You know what is observability? By using this output state. Okay, so it is the observability. Now, to be more technical, observability is the property of linkage between the output and the state. Okay, that is, it involves the matrices A and C, right? Why? Because A is the system matrix and C is the output matrix. So this is actually the linkage between the output and the state. So a linear system is said to be observable if the state vector x of t0 is found out by the knowledge of the output y of t, right? That's what we have seen. So by knowing y of t, you will be able to assess any one, the states of the input states, right? So the state variables from a knowledge of the input and the output. Okay, to be precise, by the knowledge of input as well as the output, you will be able to assess the states. Okay, So in that case also, okay, so in that case also you have a you have a matrix called as QO. This is QC refers to controllable matrix, observable matrix, and that is given by, say, C transpose. Then next is A transpose C transpose. Then next is A transpose the whole square into C transpose up to A transpose the whole raised to n minus 1 C transpose. Okay, this is the matrix. The same condition, the same thing that we have studied over here, that is, find out the rank of this matrix and check whether it is equal to n. And you don't need to find out the rank anyway. So for that, what you need to do is just find out the determinant, check whether it is equal to 0 or not equal to 0. If it is not equal to 0, then the rank is equal to the order of the system. That means the system is observable. If it is equal to 0, meaning rank is less than the order, that is, it is not observable. Okay, so this is it. So these testing using the determinant of the composite matrix QC and Q0 are called as the Kalman's test. Kalman's test for observability and controllability. Okay, hope you understood this. We'll do a problem, and by that we can come to a conclusion of this material. Okay, so we are going to do problems based on controllability and observability of a system. Now, we have already discussed what is the concept of controllability and observability, and we have a test for called as the Kalman's test, and that's the test that we do for observing the controllability and observability. So here is a system which is characterized by the transfer function yfs is equal to 2 by s cube plus 6x squared plus 11s plus 6, and you are asked to test, the question is to test the controllability and to observability. Okay, so okay, now this is how questions are usually asked. That means you will be given with the transfer function. The most simplest way of asking question is they will be giving you the matrices associated with the state model and the output equation. Okay, now may not be telling you about the method. You will be asked only to test the controllability and observability, and it is obvious that you will have to use Kalman's test for that. So now, in order to apply this, we need the matrix, right? That's what we found out from. So I'm going to rewrite what we have so far learned. That is, we have two matrices. We need to, the first step is to develop a composite matrix for both controllability, for both testing controllability and observability. So that is, you are to frame up QC as well as QO. QC is the composite matrix for the controllability, while QO is the composite matrix for checking the observability. Now QC is given by the each column will be dictated by, say, the matrix B. We know what is B. Okay, B is the input matrix, and then you have AB, where A is the system matrix. Okay, then it will be A square B, and it goes on like that, A cube B up to A n minus 1 B. Okay, so A n minus 1 B, and similarly you can also have QO as C transpose. The first column will be dictated by C transpose, where C is the output matrix, right? And yeah, next one is A transpose, that is the transpose of what? Transpose of the system matrix into the transpose of the uh, output matrix. Then you have next element will be A transpose the whole square into C transpose, and etc. up to A transpose the whole raised to n minus 1 C transpose. So these are the two matrices used for the Kalman's test for controllability and observability. Now, for both these, the test is having if the controllability is checked by this QC matrix, while observability is checked by Q0 matrix. In both the cases, what we need to find out is the determinant of QC and as well as the determinant of Q0. And if it is equal to 0, if it is not equal to 0, or if both are not equal to 0, if QC is not equal to 0, then this is called as completely controllable. Okay, controllable. Well, if QO is not equal to 0, then we will call this as completely observable. Okay, right? So just a recap of what is the meaning of controllability. By using the inputs, you can change the states of the system from one particular value to another value, while observability refers to the fact that by knowing the output and obviously the input, you can find out the states of the system at a particular time, or that is observability. So if a system need to be completely controllable, the QC, the composite matrix corresponding to the controllability, should not be equal to 0. Now, if it is a non-zero quantity, the theory behind that is the rank of this matrix will be equal to the order of the system. Okay, so if the rank is equal to, this is the basic concept of this. If the rank is equal in both the cases, if rank is equal to the order of the system, then we will say that this is controllable. And here in this case, if the rank of this matrix is equal to the order, then then it is also completely observable. So for it to be is equal to R, or the rank is to be equal to the order of the system, the requirement is this determinant of these two should not be a non-zero value, should not be a zero value. Now if it is 0, that means once if you find any one of these metrics, say for example if QC is equal to 0, that means the rank of this matrix is less than the order of the system. That's all what we need to know. We don't want to know the exact rank and so on to test this. So the thread of this is to find out the determinant. So the first step is obtain the matrices and then find out QC and QO and check whether it is a non-zero quantity or a zero quantity. Based on that, you can ascertain whether it is controllable and observable. Now, this is a kind of question that can be usually asked. So this is y of s by u of s. Now, that means in some way or other you need to get the state model. What do you mean by the state model? You need to get something like this. Okay, so the state equation is given by x dot is equal to ax plus bu, while the output equation y of t is equal to cx plus du. Okay, so some way or other, so sometimes in the question this a, b, c and d may be directly given. Okay, otherwise you will have to find out the state model. So this is a case where it is not directly given. This is an indirect way of asking question. So here the question is, you are given with the transfer function, and when you see the transfer function, as I always taught you in the previous video, the first thing you should categorize is whether this P of S is a constant or a polynomial. Now, if it is a constant, then what you just need to do is you just need to have the cross multiplication. Okay, so that is enough. So that is, you can say that your y of s divided by u of s is equal to, or is equal to 2 divided by s cube plus 6x square plus 11s plus 6, or you can call this as y of s into s cube plus 6s square plus 11s plus 6 is equal to 2 into u of s, or this is equal to s cube into y of s plus 6 times s square into y of s plus 11 times s into y of s plus 6 into y of s is equal to 2 times u of s. Okay, now from this you need to find out the inverse Laplace transform. While finding out the inverse Laplace transform, what you're going to get is, it will be d cube y of t by dt cube, okay, plus 6 into d square y of t by dt square, right? Then plus 11 into dy of t by dt, okay, then plus 6 into y of t is equal to 2 times u of t. Okay, now from this you can have the this is a canonical way of doing problem. So you can do the rest. So what is the step of this? You need to assume this y of t to be x1 and this to be a x1 dot, so that has to be assigned as x2, and this has to be assigned at x2 dot has to be assigned as x3. From this you need to find out x3 dot. Now finding that, you will get the answer as x1, 2 and x3, x1 dot, x2 dot, x3 dot matrix is equal to, since what you're going to get is a canonical controllable form, that form is actually 0 1 0. That's what we studied previously, 0 0 1, and the last row will be the negative of the polynomial, the coefficient of the polynomial. So you must not do directly, you must show the steps, okay, as we did many problems regarding this. So this will be minus 6 minus 11 and minus 6 into x1 x2 x3, right? Okay, then plus what's the next? So plus 0 0. Okay, you will be getting this as 0 0 2 into u of t. Okay, so from this what you understood is, this is actually the A matrix, right? And this one is the B matrix. A matrix is 3 into 1 3 into 3 matrix, while B matrix is 3 into 1 matrix. Okay, now the next one is how to find out your y of t. Okay, now we know that y of t we usually represent. Now how to start with? When you start, you should start like this. Y of t has to be assumed as x1, and based on those you will assign values for x1, x2 and x3. So what is y of t is equal to x1? So you can, from this you will be able to get the output equation as y of t is equal to 1 0 0 x1 x2 and x3, and this is only what you get for this this thing. So what is this matrix? This is of the form C into x plus d. There is no d, that means your d is equal to 0. Okay, right? So you got the 4 matrix. Now once you got the matrix, then you can find out the composite QC. Now the question is, when you look at the QC matrix, so first of all let us check the controllability. So in order to check the controllability, you need to develop the composite matrix corresponding to controllability is QC. Now in QC, the first element will be the matrix B. Then you have AB, A square B, up to AN minus 1. Now the next question is, you need to find out the n of this. What do you mean by n? N is referred to the order of the system. Now the characteristic equation, this is a transfer function, so the characteristic equation will give you the order of the system. The order is 3. N is equal to 3. That means you need to get how many elements? You need to get, the first is C transpose, then the first element is B, this is QC. Then next one is AB, right? And 3 minus 2, that is n minus 1. So it will be, it is A n minus 1 B. So it is A 3 minus 1, that is 2 A square B. Okay, so that means you will be having 3 columns for this. Okay, so this is B, AB and A square B. Now from this you need to find out AB. Now how will you find out? Now you have B directly given as 0, 0, 2. And what is AB? AB is actually the product of 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6, right? Into what is B? B is given as 0, 0, 2. Now let us check the order of the product of this matrix. This is actually 3 into 3 matrix, and this one is a 3 into 1 matrix. So this is multipliable, resulting in a 3 into 1 matrix. So that means it's going to be 3 rows. The answer is going to be 3 rows but with 1 column, and you are going to get your AB as 0, 2, minus 12. Okay, you may do this by yourself, the matrix multiplication. And next is what you want to get is A square B. Okay, so what you need to do is you need to multiply A into AB, right? A into AB, meaning again you need to start like this: 0, 1, 0, 0, 0, 1. So here you must do A into AB, that is 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6 into, what is AB? AB is 0 into 2, 0, 2 and minus 12. So this is again a 3 into 3 matrix. This one is a 3 into 1 matrix. So this is going to yield a 3 into 1 matrix. This is multipliable. So that will result in, okay, so that will result in, so you may just do it by yourself, calculation and so on, 2 minus 12 and 50, right? 2 minus 12 and 50. So that is your A square. So you got AB, then you have A square B. So this is actually your A square B. So this is the third column. So you have B, the first column, second column is AB, third column is A square B. So then how to find out? Now you can develop this composite matrix QC. So the first column is B. What is B? B is 0, 0, 2. QC is 0, 0, 2. The second column is AB, whose value is 0, 2 and minus 12. And the third column, which is A square B, that is equal to 2 minus 12, 50, right? So that is your QC. Now you can find the determinant of this. Now you know how to find out the determinant. Okay, finding out the determinant you're going to get is, the answer is equal to minus 8, which is a non-zero value. Non-zero value, which proves that if the determinant is 0, then the rank of the matrix will be equal to what? Equal to the order of the system, which is equal to 3. That is, since the rank is equal to the order of the system, this system is completely controllable. Okay, so the system is completely controllable, right? Okay. Now to check the observability, we need the composite matrix Q0, right? So Q0 is given by C transpose. The first column is C transpose. Then you have A transpose C transpose. Then you have A transpose the whole square C transpose. So up to Similarly, A transpose up to n minus 1 C transpose. Now, here in this problem, you will be having Q0 is equal to C transpose into A transpose C transpose up to how much? N minus 1, which is n is equal to 3. So n minus 1 is 2. That means you need to have AT square, A transpose square into C transpose. So this is the matrix that is expected. Now we have we have seen that your y of c is 0. So this is a raw matrix. So your c is actually equal to 1, 0, 0. So what must be your c transpose? Your c transpose is going to be a column matrix 1, 0, 0, right? So you got your C transpose. Now, what must be your A transpose into C transpose? A transpose into C transpose is equal to, what is A transpose? Now you know the A matrix. A matrix is this thing, and you need to take the transposes of this. Okay, so taking the transpose means converting the row into column and column into row. So that means it becomes 0, 1, 0, 0, 1, 0, right? 0, 0, 1, right? And minus 6, minus 11, minus 6 into, what is the C transpose? C transpose is 1, 0, 0. Now this is a 3 into 1 matrix. This one is a 3 into, no, this is a 3 into 3 matrix. So this is multipliable, resulting in a 3 into 1 matrix. That means a column matrix. So that is going to be, the answer is going to be 0, 1, 0, right? So you need to, again, recommend that you need to do it by yourself anyway. Then what about next? What about next? Next is AT square, right? Right? So this is AT square. AT, A transpose, the whole square, which is actually A transpose into, and this is C transpose into C transpose, or this is A transpose into C transpose, so that you will be getting this as. Now when you do, so you may just do it by yourself. So you have already this A transpose into, so this can be written as this. So already you have A transpose into C transpose is this thing. So you can have this as 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6. This is A transpose. A transpose into A transpose C transpose, that is 0, 1, 0. So this is again 0, 1, 0, right? Right? Okay. So when you do that, you're going to get this as answer as 0, 0, 0, 1. So that is A transpose C. So now you got the 3 columns for the composite matrix for observability. That is Q0 is equal to, you're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. Now when you take the determinant of Q0, determinant, it's going to be equal to 1, which is a non-zero value, meaning the rank is equal to the order of the system. And what's the order of the system? The order of the system is 3. That is, the system is completely observable. So in conclusion, you should write that, since these are both we have seen that this is controllable and this is observable. Hence this system is completely controllable and observable, and it is not necessary that a system which is controllable has to be observable and vice versa. So you need to check for all these things. So okay, both for QC and Q0, then only you should come to a conclusion. Okay, fine. So here is another question. You may do it by yourself. I'll just explain only. Okay, this is quite simple. And this is the simplest way of asking the question of controllability. Here the question asked is only about a controllability. The reason is, see, the question can be asked in this way. That is, this is a state equation is given as x dot is equal to matrix A into, so this must be your matrix A. This is your matrix A, this is matrix A, and this one is matrix B. Okay, so you have the A matrix and B matrix. Now in order to develop the composite matrix corresponding to controllability, that is QC, you require only C and A, right? C matrix, and now you require C matrix and the controllability. For developing your QC, you require the matrix A and B, right? So since QC is equal to, I'm rewriting again for you, QC is equal to B, AB, and A n minus 1, which is A square B. Okay, now how will you arrive at this conclusion? How many elements, how many columns you require? And now how will you find out the order of the system? Now the order of the system can be assessed by this system matrix. Since it is a 3 by 3 matrix, that means this dynamic system must be of the order 3. So this is the first thing that you should find out. The order of the system is 3. How will you find out the order? The order you will get from the system equation. System equation is always a square matrix, so it will be always an n into n matrix. So that n refers to the order of the system. So this is a 3 into 3 order. So 3 into 3 matrix, that means its order is 3. Now that means you must need 3 columns starting from B, A, B, and A square B. Okay, now you have your A and B. From this you may find out AB and A square B, just as in the previous problem. And finally you will be getting an answer like this. You may check for the answer. You will be getting a final answer as the total QC. The net QC is going to be 0, 0, 1, 0, 1 minus 3, 1 minus 3, and 7. And determinant m is not going to be equal to 0. So the rank you are going to get is equal to 3, which is equal to the order of the system. That means the system is a controllable system. Okay, it's a completely controllable system. Okay, so here is another question. A linear system is described by x dot is equal to a 2 by 2 matrix into x plus 1 minus 1 into r, and output equation is also given, and you are asked to find out the observability. Now we know that for finding out observability you require the need of the system matrix and the output matrix. So from the state equation you will get the system matrix, and from the output equation you will get C. And anyway here the D is 0 and you don't need anyway the 0, and your QO is going to be what? C transpose. Then next is A transpose C transpose, right? You don't need another one, right? You don't need, right? Okay, isn't it? So you don't need any other column. You only need 2 columns, because the column ends like A transpose n minus 1. Here the n is 2. Now how will you found out it? How you found out the n to be 2? N to be 2 means look at the system equation, the system matrix. System matrix is a 2 by 2 matrix, so the n is equal to 2. So it is C transpose A transpose into CT. That's enough. Okay, so this C transpose is the first column. Second column is given by A transpose into C transpose. And when you get that, you will be getting a matrix like this: 1, minus 1, minus 5, minus 1. Here also your Q0 is not equal to 0. That means this is equal to the rank of this matrix is equal to 2, is equal to the order of the system. Okay, therefore the system is a completely observable system. Okay, it is observable. Okay, so this is how, and you may do another trial. Say another x dot, it is equal to 0 1 0 0 0 1 0 minus 2 minus 3 into x plus 0 0 1 into r, and y is equal to 2 2 1. Okay, so another point to be noted is, we, even though we have used the term u for the input in the questions, it can be asked in by any letter. So when you see such equation, you must always remember that format: x dot is equal to ax plus b u, or instead of u you have r here, that's all, and y is equal to this. So y is equal to 2 to 1 into x. Okay, so here also d is 0. You are asked to perform the Kalman's test to find whether the system is completely observable. Now here also what you are going to get, so this is anyway the order of this is equal to 3, and when you find the determinant is going to be a non-zero value, which also proves that the rank is equal to. Now in some cases where you can see that at times when you whenever you find the determinant of the observation matrix or control matrix, that is q0 or qc, whenever the determinant is 0, then you can come to a conclusion that the rank is not equal to the order of the system. You cannot anyway predict the rank, but rank is not going to be equal to, say suppose in this question, if assume that if your qc is when you take the determinant, if your qc is 0, then you must write like this: r is not equal to 3, which is the order of the system, or r will be less than 3. That's all you can say. So that means that is not a controllable system. Okay, so as I told you earlier, a controllable system can be observable. Similarly, an observable system can be, a non-observable system can be a controllable. So you need to check for this whatever is being asked. Okay, right?